All right, behind me and or in front of you, you can clearly see that we have a orbital diagram drawn on the board already for you. Tell me what element it is. Do it. You can. I know you can. What element is that? Okay, well, let's take a peek. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 arrows drawn. That means 10 electrons. That means element number 10. And you look on your periodic table. What do you see? Neon. You see neon. All right, that's what we're talking about. We can predict what kind of element it is by just simply counting arrows. That's pretty easy. The other way of doing it is the last arrow that I drew is in the second level P sublevel. We're going to find that is muy importante, grande, very soon. Keep that in mind. Last arrow, 2P, and the 1, 2, 3, 4, 5, 6th position, 6th arrow in. Okay, so now that's an orbital diagram. Last time we ended up with an orbital diagram that started giving us little problems because we had some overlapping, and that was only element number 21. Element number 92 would have all kinds of overlapping. These electrons, as these energy levels get larger and larger, can be moving all over the place, and there's an overlapping. And the reason for that, if we go back to Bohr, Bohr specifically said that there were going to be electrons in energy levels that are orbiting around the atom, and that's not the way it is. Modern atomic theory has the model set up that these electrons are not locked into a particular orbit. There's sublevels with those energy levels, which Bohr didn't have in his model. And these electrons have a probability of being in certain places at certain times, and it's called a probability cloud. So these orbital diagrams are where the electrons are usually going to be found unless they become excited and shifted energy levels. They're usually going to be found in these spots. So the thing about orbital diagrams, as we have said, they're cumbersome. So how could we make it easier to show where these electrons are hanging out? Okay, let's go back to the carbon. Carbon, I'm going to draw this in quickly here. That's a 2. Carbon looks like this. Yes, it does the hybridizing thing, but I'm not going to do the hybridized carbon orbital. This is the orbital diagram for carbon. 1, 2, 3, 4, 5, 6 electrons, and we are showing where those electrons would be hanging out before the hybridizing. All right, that's a little bit slow to do. I'm going to draw what's called an electron configuration, not an orbital diagram, an electron configuration. The electron configuration for carbon is going to look like this. Two S first, and then 2P2. That's called an electron configuration, and it shows where the electrons are, what energy level they're in, what sublevel they're in, and how many of each there are. Now take a look and see if that doesn't look just like the orbital diagram in terms of where the electrons are. We have 2 electrons in the sublevel S of energy level 1. We have 2 electrons in the sublevel S of energy level 2. We have 2 electrons in sublevel P of energy level 2. This electron configuration is showing in an easier way where these electrons are hanging out compared to the orbital filling diagram. Now I know what you're saying to yourself in the studio audience, kids. You're saying, well, wait, I need to draw that out first, and then I can draw this from that. Isn't that what you did? You just looked at this and drew that out. Actually, not true. I mean, you can do that, absolutely, but you don't have to draw an orbital filling diagram in order to make an electron configuration. There's a way of doing it. It's called reading the periodic table. Reading the periodic table is like a good book. You sit down and a glass of wine, read the yeah, absolutely. Absolutely you can. It's a good read. Now I'll teach you how to read that periodic table very shortly. Let's go back to our aluminum that we had. And the aluminum, if we had a larger board in the classroom, I would have set these up over on the right and left them there. But so we have 1S, 2S, 2P, 3s. And there's 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, that was our orbital filling diagram for aluminum, 13 electrons. And if I'm going to draw the electron configuration from this, that will be 1s2, 2s2, 2p6, 3, 4, 5, 6, 3s2, and 3p1. Once again, you're probably saying, well, I can't do that. That does look faster. Yep, that's going to be faster for me to do, but I can't do that unless I've got this in front of me to figure it out. No, 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 no. All right, how am I going to draw these electron configurations? Well, let's get ourselves a periodic table. All right, get a periodic table, and then we will come back and show you how to write an electron configuration without having to do an orbital filling diagram. All right, BRB.